Today we're going to start out with a couple of Bellwork problems, and then we're going to do a continuation of the investigation into rational and irrational numbers that we started in our last lesson. So first of all, we've got another table of values, and as we advance this and look forward, we notice that in the x direction and in the y direction, each number jumps up by 2, which means they jump up by the same amount. Now, they don't have to jump up by 2 on each side, but the key is that each side is jumping up by the same amount from step to step to step. So because they do jump up by the same amount on each side, it's considered a constant rate of change. Therefore, it is considered to be a linear situation or a linear function. And now we need to write an equation for it. So to do that, we notice that we've got a constant rate of change of 2 over 2. So we have to write y equals 2 over 2x plus, and then we notice up here on our pattern that if we actually reverse our pattern and go down from 2, we'll end up at 0. And we know that when x is 0, the y value at that point is going to be our y-intercept. So we notice that this goes down by 2, this goes down by 2. So that means that our y-intercept is 5, and there we are. Now we can simplify this slope of 2 over 2 to be 1. So our final simplified equation is y equals 1x plus 5. All right, so let's continue on with our discussion of rational and irrational numbers. So we mentioned already that the natural numbers are the counting numbers starting at 1 and going up. The whole numbers include the natural numbers, but also include another number, 0. Then we included the integers, which include all the natural and whole numbers, and as well the negative counting numbers. So that's what we call the set of integers. Then we mentioned on our last lesson the rational numbers. That's all the whole numbers, integers, and natural numbers are considered rational numbers, as well as all of the fractions and decimals that lie in between them, as long as the decimals and fractions, or at least the decimals, are repeating or terminating decimals. So those are kind of some important definitions to help us classify this. All right, then we mentioned that there's also some numbers called irrational numbers that represent a non-repeating and a non-ending decimal. These are kind of strange numbers, and pi is a classic example of that. So here's what pi, the first few digits of pi, looks like. But pi actually goes on as forever, as far as we know, never terminating or never repeating. And so you can find all kinds of numbers lined up somewhere in that string of digits of pi. All right, so now we want to talk about a couple of things we might see in this lesson. First of all, we might be converting a repeating decimal or into a fraction. So, for example, the repeating decimal 0.33333. So in order to turn that into a fraction, we can't just write 3 over 10 because it repeats. So what we can do is we can do a little exercise where we say x equals 0.33333. So we just let our decimal equal x. Then we multiply both sides of our decimal, or of our little equation, by 10. So we end up with 10x equals 3.3333 repeating. And then we subtract the first equation from the second one. So we subtract this top one from this one. And that ends up being 10x minus 1x, which is 9x. And all of these decimals minus these decimals leave us with just 3. So then we divide both sides by 9. And so our final answer is 3/9, which simplifies to be 1/3. So in other words, the repeating decimal 0.33333 simplifies to be the fraction 1/3. So let's continue this a little bit further. If I have 2 digits that repeat, like I have in this case, then I have to multiply, and when I set up my little equation, x equals 0.2525 and so on, then I have to multiply by 100 instead of just 10 because I have two digits that repeat. So when I do that, it moves the decimal 2 places to the right, and then I subtract the smaller equation from the bigger equation, and I end up with 99x equals 25. When I divide both sides by 99, I end up with 25/99ths for my fraction. So I want you to kind of keep in mind there what happened then. In our first example, when we had one digit that repeated, we ended up with 3, that digit, over 19. Now we've got two digits that repeat, and our answer has those two digits over 2 nines. So our little shortcut on this then would be, if you have 3 digits that repeat, then you just write down the 3 repeating digits, whatever they happen to be, and underneath that you put 3 nines. So that's the secret formula. So however many digits repeat, you write that on the top. And then however many digits that is, you write that many nines underneath it, and you have turned a repeating decimal into a fraction. Now there are a few repeating decimals that are a little more complex than that, but this will take us as far as we need to go for this class. Some of the other things that we might be doing is comparing fractions by finding a common denominator. So let's do that. So we've got 8 ninths and 5 sixths. We notice that the common denominator between those two is probably going to be 18. So I'm multiplying the top and the bottom of each fraction by a number that will give us that common denominator of 18. And in the first one, we end up with 16/18. In the second one, we end up with 15/18. And so we notice that the first one is slightly bigger than the second one, so we do greater than. If we try another one, we notice we've got 8 and 10, so what would be a common denominator there? Well, we have to go out a little bit further. It's a little more difficult to find it, but we take the multiples of 8 and the multiples of 10 out far enough until we find a common one, and we notice that 40 is the number we're looking for. So we have to multiply our fractions by numbers that will create a common denominator of 40. So the first one we multiply the top and bottom by 5, the second one the top and bottom by 4, and we end up with 25/40ths and 28/40ths. So we know that 25/40ths is less than 28/40ths, so that means 5/8 is less than 7/10. All right, we could also continue this type of line of reasoning with a problem like this. We've got to order these fractions from least to greatest. So we're going to get a common denominator once again. So in this case, we've got to take all three numbers, all three denominators, look at their multiples, and keep going out until we find a common one. And we notice that the common denominator in this particular case happens to be 24. That's the least common one between them. So then we end up having to multiply each fraction by a number that will produce that common denominator of 24 in each of their denominators. And so we end up with 1/3 equals 8/24, 1/8 equals 3/24, and 1/6 equals 4/24. Well, we know that 3/24 is the smallest, so that means that we put 1/8 is our least number. Then we notice that 1/6 or 4/24 is our next smallest, so that comes next. And then 1/3, which is 8/24, is our biggest of the three numbers, so it comes last in our list. Now we've got a few more. What if we have 1/5, 3/10, and 5/20? Well, we notice that we need to multiply the top and the bottom of the first two fractions to create a common denominator of 20. And when we do that, we end up with 4/20, 6/20, and 5/20. So we need to move this 5/20 to the middle position, which means that we will end up with 1/5, 5/20, and 3/10 is the order of these initial fractions from least to greatest. Example here then, the question is, can this be written as a fraction? So if we look at our first one, it is a terminating decimal. So if it's a terminating decimal, then yes, it can be written as a fraction. And the reason is because it's a terminating decimal. The second one is a repeating decimal. So if you have a repeating decimal, as we've learned earlier in this lesson, you can also write that as a fraction. So yes. The last one, on the other hand, is the square root of 3. Now, if we take the square root of 3, we notice that it's a strange decimal that goes out, never repeats or terminates, but it just keeps going in a strange pattern like pi. So it is one of those who cannot be written as a fraction, and the reason it can't is because the decimal neither terminates nor repeats. So that's how you will answer any of those questions that come up on our assignment. So thank you very much, and good luck on your Alex assignment today. So we're going to ask you to do rational and irrational numbers, part 2 on Alex. So good luck, and thank you very much.